Hello everybody, I'm going to teach you how to make an XP farm in the nether. Oh no, sorry, we're going to talk about polymers. This is GCSE content, AQA, paper 2 in the organic section. Most people have been asking about condensation polymers. We'll get to that very, very soon. It's worth just having a quick look at addition polymers though, because they're a thing too, and so that we can then hold them up side by side and talk about, what the differences are and so on. So let's start with the simplest possible alkene, ethene. You know that the CC double bond is the main event here. It's the functional group of this molecule. It's the reactive bit, basically. We'll also deal with propene shortly. So let's put a 3-carbon alkene in. It's got 3 carbons. It's got a double bond in there somewhere between 2 of its carbons, and every carbon has 4 bonds. So that's C2H4. This is C3H6. And we'll have a look at another one just for the love of it. You don't need to know the name of this. However, I'm going to give you the name of it anyway. There it is. Now, what might the name of that be? We don't really need to overthink naming of organic molecules in this much detail for GCSE, so I'm not going to go on now in this revision video about loads of A-level stuff. What we can work out though, for a start, it's an alkene. It has a CC double bond in it, so its name will end in ene. It has 4 carbons, so that would be bute, MEPB, meth, eth, prop, bute. So this is a butene. There are some alternatives. The CC double bond could be in the middle there, or it could be at the end, at the other end where that Cl is. On top of that, there's this Cl. We're going a bit further than we need now. It could be called chlorobutene. You don't need the name of this one. I'm going to give you the name anyway, just for the love of it. This would be 1-chloro-but-1-ene. You definitely won't have to name things like that. You should recognise that this is propene, and this with 2 carbons is ethene. Anyway, the purpose of this little bit on addition polymers is to make sure that you can definitely construct a repeating unit for any such example and recognise what they're all about. So in every single case, in these 3 cases here, that bit which I'm circling is what I'll call the reactive bit. Fair enough, that Cl complicates it, but let's not go into A-level again now. So the alkene carbons, that's where the main event happens basically. So let's draw polyethene, polypropene, and poly that thing there, just to check if we can. If you want to pause the video and have a go for yourselves, do. Else, just watch along with me. I'm not going to spend ages on this. So ethene, the simplest one. Polyethene then, for a start, that's its name. It's just poly brackets, the name of the alkene it came from. It's not actually an alkene once the reaction's taken place. The double bond carbons end up singly bonded together. Trailing bonds, this is something you'll hopefully already be familiar with, the idea of using a brackets and N notation. And each carbon in ethene has just got 2 H's on it, and that remains the same. That never changes actually. Whatever was there at the beginning is still there at the end. You'll see that in action in the next 2 examples. So there's polyethene. And if we had to balance an equation for that, we could say something like N ethenes. Now again, remember, N is a large number here. These polymers are big molecules. Many, we're talking about like tens of thousands kind of scale, or greater than that even. Many molecules of these monomers, which in this case it's ethene, bond together, or react and bond together to make one large polymer molecule. Many bricks make one big building. Many of these units make one big, object, a polymer. Okay, that's a balanced equation. N of these make something that has this repeating unit. There is a bit more to it, as in the ones at the end of the chain. What do they have there? There's more to it, but that's all we need. Next job. This one catches people out. We see it all the time, propene. The problem, the mistake that we often see is students trying to do a repeating unit that's got 3 carbons in it from propene. I can kind of see why, but they're missing an important point. That's never going to be correct, okay? It's all about this double bond here. The double bond carbons, one of them's got 2 H's, the other's got a H and a CH3, and it's these double bond carbons that bond to another pair of those double bond carbons on a nearby molecule. So it's the CC double bond carbons which chain together, and everything else is just an attachment. So now I'm going to go ahead and draw polypropene. Here we go. We've got a double bond carbon that has a H and a CH3 on it, and the other one has a H, just 2 H's on it. Many of those react together to form one big unit. Those double bond carbons become singly bonded. The trailing bonds in the end, as seen there. One of them has 2 H's on. the other of those carbons has a H and a CH3. That is the correct structure of polypropene. Okay, it's actually not an alkene anymore, it's saturated now, it's only got single bonds between its carbon atoms, but we still call it polypropene. We just appreciate the poly implies it's actually reacted to make something which is no longer unsaturated, okay? It's undergone an addition reaction where lots of these have added together, or many monomers have bonded together to make one large polymer molecule. Last one. So let's follow that format. This double bond carbon, this pair of double bonded carbons here, one's got a H and a Cl on it, the other's got a H and an ethyl group, a CH2, CH3 group, which would be that. Okay. We could write a C2H5. So one's got a H and a Cl, one's got a H and an ethyl. Let's follow that format now. So this repeating unit is 2 carbons wide. Again, those are the double bond carbons, brackets N. One of them had the H and a chlorine atom, one had a H and C2H5 on it. There's the correct structure, and we'd call that poly 1-chlorobutene, something like that, but the name is or polymysteromaleine or something stupid, okay? There we are. Now, we'll come back to these when we compare, but we'll have a quick look at condensation polymers, okay? Pause that. Right, back to condensation polymers. So, there are 2 types of condensation polymer. We've got polyesters, which you'll have heard of just from looking at the labels on your clothing, and possibly also you'd have heard of polyamides before studying it, okay? So let's have a think about the functional groups involved here. First of all, how do we make an ester? Well, we need an alcohol and a carboxylic acid. That's the only way that we've got on GCSE chemistry of making an ester. Those 2 functional groups react. I'm just going to pop a CH3 on there and a CH3 on there. This won't be making a polyester. This is just going to be a simple ester. But the point we'll make here, we can then extrapolate to ones that actually do make polymers. So this alcohol, written back to front, methanol, and that ethanoic acid there, they react. You don't need to know which way round it is, so I'll tell you anyway. The OH from the carboxylic acid gets snipped off as part of this reaction. There it is. And the alcohol's hydrogen gets taken off as well, forming a water molecule, okay? In the process of doing so, that means there's space on this carbon to bond to something, there's space on that alcohol O to bond to something, they bond to each other. So you get an ester, that is the ester functional group there, the bit that I've put in the box, and it's a condensation reaction, meaning HOH, better known as H2O, water has been pushed out. Now that's not a polymer, there's no more potential for growth there. We'll come back to that in a second. That is an ester from a carboxylic acid and alcohol. Amides. Okay, so again, let's just do a simple amide first. Dare say simple for this one, but then we can extrapolate this to a polyamide. Once again, a carboxylic acid, so I've just closed it off at this end. I've put ethanoic acid and an amine. Amines are less well remembered because they only crop up in this little section on polymers going into amino acids. We're going to mention amino acids and proteins shortly as well. Now, again, I've written it kind of back to front, but let's have a look. If an alcohol is an OH bonded to a carbon, an amine is an NH2 bonded to a carbon. More conventionally, we'd write the formula for that chemical as CH3NH2. Just like this alcohol, methanol, would normally write as CH3OH. The reason I've drawn it back to front is just so you can keep track of what goes where. Same story as before. The OH off the carboxylic acid gets taken away, and a H from this thing over here was an alcohol losing its one H. This amine loses either, but only one of its H's. So as before, that means there's room on this C double bond O for a new connection, and NH2, just like the OH before it, loses a H, and what's left, so NH2 becomes NH, bonds in its place. They bond together. And again, the OH has dropped off the carboxylic acid, a H has dropped off the amine. It's a condensation reaction. That's what we call it when water gets produced as a product. So I drew the box around the ester linkage here. That is the amide linkage. Less likely you'll need to quote that or recognize it, but it is on the spec, okay? Now, how does this relate to polymers? Because these are small molecules with a definite and small number of atoms. They don't have a repeating unit per se. Well, basically, we're just going to do this again. except the carboxylic acid is going to have 2 carboxylic acid groups, and the alcohol we'll use will have 2 OHs on it, so that once one pair have connected up, there's something at the other end to grow. And once we've said it about esters, we'll then just say, yeah, look, and it's the same for these. Then we'll look at amino acids and proteins as well. So now let's make this a polyester. Making a polyester. So the monomers vary. I'm going to give you a specific example first, but then I'm just going to show you what's on the spec, where they just use a box basically as a placeholder for some atoms. So here is a complete molecule. I'm putting CH2, in between 2 carboxylic acid groups. You can see that, 2 COOHs with something in between. On the spec, it's actually printed, they've just got a box. And the box doesn't have to be CH2, it could in real life be all sorts of different options. It could be 4 CH2s, or it could be like a benzene ring, it could be all sorts of weird, wonderful stuff. It's just a placeholder for atoms in the middle. So I'm going to use boxes now, but I've just given you an illustration of what the box represents, just some atoms between the 2 groups, okay, to make longer or shorter units. This is one of our monomers. Here's the other monomer. It's an alcohol. Again, I'll just use CH2 as a spacer group between the 2 reactive bits, the alcohol functional groups. And again, that could vary. It could be anything you like, really, that's sensible. So again, we'll just use this as a placeholder. We'll choose a box to say, yeah, some atoms, something that spaces them apart. Now, when they react, first of all, I'm going to make the dimer. Okay, so here are 2 monomers coming together. They're going to make one unit, which we could call a dimer. One end of the molecule doesn't react, so I'm going to leave that carboxylic acid intact. Again, I'm just using the box now for convenience. The point is that carboxylic acid group has reacted in a condensation reaction and kicking out a water molecule as part of it. There's the carboxylic acid's contribution to what will be a water molecule. As for the alcohol, we saw this earlier on. It loses a H. There's a complete H2O now. We don't need to worry about how the atoms get transferred. We just know that's the pattern of what happens. And again, put a real thing in there if you like a CH2, but there's a spacer group, and then you've got the rest of it. Now, this end of the molecule hasn't reacted yet, so that's still got its OH alcohol group in place, okay? So there's the dimer. Ultimately, the purpose of doing this is now to show you how this links to a polymer. Imagine that another one of these carboxylic acids came along. It can't react with this end because it's 2 of the same functional group, and that one doesn't react with itself. An alcohol can't react there, but one of these carboxylic acids could react with this alcohol here. So now it's better off a whiteboard, but I'm going to make the trimer. The point is that would involve that H dropping off and a carboxylic acid's OH dropping off as well, and we could build another monomer into the chain. And at that point, another alcohol could come along and react with either end and connect up again. So the repeating unit for this would be to show both monomers connected up in the middle of the structure. So there's I've done it all in one coloured pen now. There's the carboxylic acid bit. There's the contribution from the alcohol. Here's the ester linkage that holds those 2 together. And at the other end of the repeating unit, you've got the makings of another ester linkage. That's what happens to carboxylic acids when they react. In this way, they lose their OH. That's what happens to the alcohol, it loses its H. Now, in terms of a repeating unit, that's it. We could put the brackets and the N on, but then at that point, you need to balance it with N. Let me just turn the page and show you what this would look like then. So if we add N of the carboxylic acid and N of the alcohol, which again it's a diacid and a dialcohol, then we'd get something that has N repeating units, where the repeating unit is the sum of these 2 for a start. So again, I've taken off an OH there, keep track of that. We've got, I've taken off another OH here, keep track of that. Here's the alcohol bit, I've just taken off a H there, and I've just taken off a H here. So for every N of each type of monomer, N of this and N of that, you'd get one repeating unit with that pattern. It's just those 2 together N times, and then we get 2N H2O. For every one of these, I'm getting 2 waters. because there's an ester linkage there. That's one of the waters. There's an OH and a H from the ends. That's where the second H2O comes from. The problem with this is it's long, isn't it? There's a lot to draw. There's a lot to keep track of. The essential knowledge here really is, first start recognizing functional groups, alcohols, carboxylic acids, esters. And secondly, being aware of how they bond. When they react, H2O gets kicked out and an alcohol and acid become an ester, okay? Now let's look at polyamides. It's basically going to be this again. So I'll try not to repeat myself too much. Making a polyamide. And then this will take us into the final section on this, which is about amino acids and proteins. So again, it's essential knowledge here that is a carboxylic acid, that this group, an NH2, is an amine. Again, it's less familiar. And whether we need to know the name of it or not, the connection they make is called an amide. Okay, amine, amide, carboxylic acid. So let's do the same thing again. I'm just going to use boxes to space apart two COHs and two NH2s in two separate monomers. Again, pause and have a go for yourself if you want to. I'm going to just get on with building mine now. So my monomers first of all. A diacid, just using a box because I can't be bothered to draw CH2, whatever every time. An amine. I'm going to expand this out just so you get a chance to see it. I could just write NH2 or H2N there. I'll expand it out because you can really keep track of the H's disappearing. N of these react with N of those, okay? To give. I'm going to go straight in with the repeating unit this time rather than a dimer, okay? So this COOH in the middle reacts and loses its OH. This NH2 over here loses a H and connects up. So NH2 becomes NH, COOH becomes CO. That's where the missing OH and H have gone. The NH2 that has now reacted was bonded to the rest of its molecule. And if I did want to draw the dimer, I'd stick a H on the end there. But I'm going to leave it trailing because the idea is lots of these react with as many, another large number of those. So there's N and N for many. The carboxylic acid, CO, was bonded to the rest of the molecule, which had another COH at the other end, and again it's reacted as well. So there's another OH missing there, there's a H missing from over here. So there's N of these, react with N of those, to make one unit of the repeating unit, and again plus 2N waters. Okay, that's a balanced equation now, in that the OH and the H, and the OH and H from here are represented in the balanced equation in terms of N monomers in the first place. So yeah, it's awkward. That is the amide linkage. That's what this is about. Now, before we look at amino acids and proteins, just to quickly compare polyalkenes, addition polymers, with condensation polymers. Obviously, condensation polymers, there's more to draw, which is why people generally want some help with it for revision. In terms of biodegradability, let me just draw two repeating units of an alkene. It doesn't really matter what's there, just pick your favourite example from earlier on, H's or the other things we had CLs and whatnot. I'm just going to put etc. Now, this addition polymer has got strong carbon-to-carbon bonds holding the chain together. And just trust me, for a variety of reasons, they're difficult to break, okay? And therefore, these don't biodegrade easily. Enzymes have a hard time latching onto them and trying to break them down. They generally persist in the environment for a long time. So things like plastic bags made of polyethylene are an environmental problem, mostly because they just persist in landfill. They don't rot away. They just break it down into smaller and smaller little microplastics. Now, I've got to be careful. I'm only going to bother showing you an ester. And there's just a fragment of a polyester, again, where there's just more of these further down the chain. Better be careful, because I've just said these bonds are strong and difficult to break. These bonds are also strong, all right? The difference is that they're they're formed by condensation reactions. It's not about the bonds being weak. It's not about bonds being weak. But if water was popped out, water can be popped back in. Nature happens in aqueous solution, as in living systems are all water-based, okay? And basically, all the enzymes, all the little decomposers, bacteria, whatever, don't have a difficult time latching onto these. So there's not really many enzymes out there that can break down carbon-to-carbon bonds. However, this is really natural stuff. We're made of esters and amides and all sorts as well. A lot of what we absorb and eat has got these kind of linkages in it. And it's not about weak bonds, but it's the idea that a water molecule could be put back in and these ester linkages could be broken apart. So I'm splitting my waters with the red pen here and I'm putting them back on. There's a complete unit of a monomer. There's a broken off bit. These can be easily broken down, okay? The word that the A-level guys would use is hydrolyze. It's probably a bit late in the day to be introducing that word now. So let's just say easy to break down, easy to digest, easy to have the water molecule put back in. And so they just do biodegrade. We don't have to worry too much about why that is. Just trust me that if water comes out, water can go back in. And in living systems, enzymes, water is everywhere. So that's not a complete oddity. So they're biodegradable, which means they're potentially better for the environment. At least it might take decades for it to rot, but it will eventually. That's the idea. Right now, and it also means you can recycle the monomers. You could break it down and get the monomers back, and then reuse them. Recycle by reusing. Maybe that helps. Final thing on this, then we're about to be hitting the 25 to 30 minute mark, so we better call it. Amino acids and proteins. So there are 3 naturally occurring monomers that you have to know about. Amino acids is for GCSE chemistry are one of them. Now look at that. We've just seen these functional groups. Carboxylic acid, amine. They react together to make amides. Rather than having 2 monomers, both of which has, I've lost a piece of paper. Rather than having 2 monomers, where one's got 2 acids and the other's got 2 amines, why don't we just have one monomer where like it's got both, one each at either end? That's precisely what an amino acid is. An alternative to that, not amino acid, would be going to the polyester one. Why don't we have a monomer that's got an alcohol at one end and a carboxylic acid at the other? That's not on the spec, but it's the kind of thing the examiner could really challenge us with, because it's like, well, that could react with another one of itself, because this acid group could go with that alcohol group. It might even loop around, which would be a crazy thought. But like another one of these could connect up here in a condensation reaction. And, that OH could go, that H could go. They could make an ester linkage. I know how messy that is with the scribble now. They could link up, okay? And that's precisely what amino acids do. Many of these dictated as in specific which amino acids and in what sequence, dictated by DNA. Many of them do. So the repeating unit for this amino acid, which by the way, might as well tell you is called glycine, would be, again, to show the NH2 losing one of its H's. The rest of it in the middle, that was just the box before. I'm actually writing a CH2 this time. The carboxylic acid losing its OH. That would be the repeating unit. Make sure the bonds are trailing outside of the brackets for polyglycine. Okay. N of these react to make one big one of these, and for every one of these there's an OH that's disappeared from here, a H from there, so there'd be NH2O. It's not 2N this time, notice. An OH is missing and a H is missing. Naturally occurring polyamino acids are called proteins. So this one we could call polyglycine, only because you were told that that's called glycine. You're not expected to recognise that's glycine. That's the name of it. But naturally occurring. So for a naturally occurring protein, one which is coded for by DNA and transcribed and whatnot at the ribosomes, I know that's creeping into biology there. The general formula for any amino acid is it's not actually. It's CH2 becomes CHR, because the R group can vary. There are 20 odd naturally occurring amino acids, and the difference between all of them is just whatever that is there that's on this carbon. They've all except one have got a H and an R group. There's the repeating unit for it. So this would have been an NH2. That was a COOH. That there is just polyamino acid. Proteins are long polymer chains with this repeating unit. But R is one of several possibilities, 20 odd, and DNA dictates which one goes next in the sequence. But at one end of the chain, you've got what's called the N-terminus, where that's actually intact. and at the other end of the long polymer molecule, you've got the carboxylic acid. Okay? And then they fold up and link up and do lots of weird and wonderful foldings, but I'm not going to go into that now. Now, just since I mentioned it, there are 3 naturally occurring monomers and naturally occurring proteins to know. Amino acids is one of them. They polymerize to make proteins. I'm only going to say it verbally. There's also sugar, glucose, which polymerizes to make cellulose or starch. And there is nucleotides, which are like the DNA bases with the sugar and phosphate attached, which polymerize to make DNA, which has got that double helix shape. So may I suggest off the back of this, you spend a few minutes checking your revision guide and your class notes for what those naturally occurring polymers were, because you're expected to know the names of nucleotide, glucose makes cellulose, and amino acids make proteins, and you know that nucleotides are for DNA, okay? Hope that's been helpful. It's a tricky topic. It's mostly just drawing and recognising and keeping track of where the OHs and the H's drop off from. Okay, good luck with everything.